All right, let's dive into a topic that can feel a little tricky at first, but is actually super powerful once you get the hang of it. Inverse trigonometric functions. We're going to master them today. Let's get right to it.
So, to really get why these functions even exist, we have to ask a fundamental question. What is the single biggest problem with our regular everyday trig functions? The thing that stops us from just flipping them inside out like we do with other functions.
And here it is. This is the problem. Think about the graph for sine or cosine. It's that classic wave, right? And it just goes on and on and on forever. So what happens if you draw a horizontal line anywhere on that graph, say at y equals 0.5? It hits the wave once, twice, 100 times, an infinite number of times. That's a huge issue. It means one output has endless possible inputs, which means the function is not one-to-one. And if it's not one-to-one, you just can't find a simple inverse. So let's just nail down the core idea here. It's a total role reversal. A normal trig function, like sine, you feed it an angle, and it spits out a ratio. Well, the inverse function, we call it arcsine, does the exact opposite. You feed it that ratio, and its entire job is to tell you what angle created it. But how does it give you just one angle when we just saw there are infinite possibilities? This brings us to the really clever solution. We have to somehow tame those infinite waves. And we do it with this brilliant mathematical move called restricting the domain. Honestly, this one idea is the key that unlocks this entire topic. So what on earth is domain restriction? Well, it's pretty much what it sounds like. We basically decide to take a pair of scissors to that infinite wave. We chop off a single, specific piece of it, a piece where the function does pass the horizontal line test. By agreeing to just focus on that one little segment and ignore the rest, we create a new, well-behaved function that we can finally actually invert.
So what does this look like in the real world? Well, by chopping up our original functions, we create brand new rules for the answers we're allowed to give. These are the output ranges for our new arc functions. And let me be clear, these rules are non-negotiable. You absolutely have to commit them to memory. And here they are, the big three. For arcsine, your final answer, the angle, must be between negative pi over 2 and positive pi over 2. That means your answer has to live in either quadrant 1 or quadrant 4. Got it? For arccos, the angle has to be between 0 and pi. So that means quadrant 1 or 2. It lives in the top half of the unit circle. And arctan is pretty much the same as arcsine, it just has parentheses instead of brackets because of those asymptotes. These ranges are the absolute law when you're doing inverse trig. All right, that's enough theory. Theory's great, but let's get our hands dirty and see how these rules actually save the day when we're solving problems. We're going to put this all into practice right now. Okay, let's try arcsine of negative 1/2. My first thought is always ignore the negative for a second. What angle gives me a sine of positive 1/2? Easy, that's pi over 6. But our input is negative, so where is sine negative? That's quadrants 3 and 4. Now here comes the new rule. The answer for arcsine must be in quadrant I or 4. So where's the overlap? Quadrant 4. We take our reference angle, pi over 6, and put it in quadrant 4 the right way, which gives us our final answer, negative pi over 6. Now, this is so important. This is the number one trap. You might be tempted to say the answer is 11 pi over 6. And you know what? The sine of 11 pi over 6 times is negative 1/2. You're not wrong about that. But that angle is outside our mandatory restricted range. It's illegal. You have to give the answer that's inside the bubble, which is negative pi over 6. Please lock this concept down. Okay, what if you see something like this, a function inside a function? Don't panic. The secret weapon is always to draw a triangle. The stuff on the inside, arcsine of 3/5, is just some angle. We don't know what it is, so let's call it theta. This little equation means that the sine of theta equals 3 over 5. Well, sine is opposite over hypotenuse, so we just draw a right triangle with an opposite side of 3 and a hypotenuse of 5. Hey, that's a 3, 4, 5 right triangle, so the adjacent side has to be 4. And now the problem is super easy. What's the cosine of theta? Just look at your triangle, adjacent over hypotenuse. It's 4 over 5. Done. Now let's get wild and throw a variable in there. Don't freak out, the game plan is exactly the same. The inside part, arc cos of x, is just some angle theta. That means the cosine of theta is x, which is the same as x over 1. So we draw our triangle, adjacent side is x, hypotenuse is 1. We use the Pythagorean theorem to find that last side, and it turns out to be the square root of 1 minus x squared. So what's the tangent of theta? Opposite over adjacent. And there's our answer. We just turned a complicated trig expression into a simple algebraic one. Pretty cool, right?
So you might be sitting there thinking, okay, this is a neat trip, but why do I really need to get this down? Well, let me tell you, this isn't just some random topic in precalculus. It is a critical building block for what's coming next. Here's a little spoiler alert for your future in calculus. You're going to see problems that look like this monster. They're called integrals. And guess what the answer to this thing is? It's just arc sine of x. Seriously. If you understand what arcsine is and how its restrictions work, this becomes a surprisingly simple problem. But if you don't, it's a massive roadblock. Trust me, mastering this now is going to make your life so much easier later on.
So we took these infinite, chaotic, repeating waves, and we found a clever way to tame them, to pick out one single unique angle from a ratio. We basically figured out how to undo a wave, so I'll just leave you with this final thought. Now that you have this incredibly powerful tool in your toolbox, what new things could you possibly measure? What kind of problems can you solve now that were impossible before?